My name is Christian Aparicio, and I'll be going over today's tutorial with you. This is a continuation of a long workshop series. The goal is to optimize a composite coupon. In this tutorial, what we are going to be focusing on is crafting optimal ply shapes and then performing a ply number optimization with MSC Nastran Sol 200. Now, here, I'm just flipping over the various workshops that we've gone over so far. Again, today we're going over phase D, where we get to perform this ply shape and ply number optimization. In the next workshop, we're going to be working on the final workshop, which is a stack and sequence optimization. Here is just a diagram of the ply shapes we're going to be building for this workshop. And here, just as a reminder, the previous workshop was to prepare the data to construct the ply shapes. Here we ended up creating a set of bulk data files with tomvar entries, and we developed or created these ply files. We're going to take this data and we're going to feed it, we're going to input it to the viewer web app. It's in this viewer web app where we are going to be able to create these different ply shapes. Now, the analysis model is still the same analysis model we've been working with so far. We fixed or clamped the composite coupon on this edge, and then on the opposing free edge, we have two load cases as shown here in this diagram. The pcomp entry. So I'll repeat the same thing I've said in the last few workshops. The first 4 layers are fixed. So here, let me write down fixed. So by this, I mean that we've taken 4 layers for 90, 45, negative 45, and 0 degrees. We've created these layers here with the thickness equal to the ply thickness of 0.125 millimeters. These plies are not going to change during this optimization. The ply thickness will remain constant throughout this entire workshop series. The next 4 layers, these 4 layers are allowed to vary during the optimization. So this 0.25 thickness, this will change during this whole optimization procedure. Now, there are various reasons why I do this. If you refer to the appendix, let me jump out of here. If you refer to the appendix that's available in the PDF file, I go into more detail regarding why I do this. Why do I have a specific format for the pcomp entry? So this is located in the section called Consideration of pcomp. So again, if you have a question on why I format the pcomp entry in this very specific way, refer to the last section in the appendix. Now let me go back to the introduction slides and we'll go ahead and continue on in a moment. Now, on the next slide is just an overview of the various ply shapes we're going to be creating. For the 90-degree layers, these are some of the ply shape candidates we're going to build. You can see we're going to create this ply shape that's close to the fixed edge or the clamped edge of the composite coupon, and then for the hole we're going to create a separate ply shape for the hole. The blue color means that that's where the ply shape exists. The gray indicates where the ply shape does not exist. And then we're going to repeat the process for the 45-degree layers. One thing about the 45-degree layers is that we have both positive and negative 45-degree layers, and we want to maintain a balanced laminate. So we're going to be creating identical ply shapes for both the positive and negative 45-degree plies. For the 0-degree layers, we're going to create more than 3 ply shape candidates. We're going to create this fully continuous ply shape that spans the entire coupon. And then we're going to go ahead and create the second ply shape candidate, then this third shape ply candidate around the hole. And then we're going to create 2 additional candidates for the fixed edge and the hole. Now, as always, please take some time to create your problem statement on a piece of paper. Do not immediately run to the software and start to press buttons and try to configure your optimization. First, list out what your variables are, list out what your objective is, and list out what your constraints are. Once you create this list, then move on to configuring your optimization. So what are the design variables for this optimization? So we're going to create these various ply shapes in a moment. So here is maybe our first ply shape. Our next ply shape might look like this. And then for the hole, maybe we'll create a ply shape like this. So you can think the hole's here. Now, once we create these ply shapes, we need to duplicate or repeat these ply shapes depending on what the ply number optimization tells us. So as an example, here, let's suppose this ply shape, we're going to represent it with variable y1. This variable is y2. And then this ply shape is variable y3. At the end, we might get told that we need 10 plies of this ply shape. We might need 3 plies of this ply shape, and then here we might need 5 plies for this ply shape. So that's why we have 11 variables here. We are going to construct 11 unique ply shapes for the 90 degree, the positive 45 and negative 45 degree layers, and the 0 degree layers. So in total, we're going to have 11 ply shapes, and then we're going to use the ply number optimization to determine how many of each ply shape do we need. Here on the right, our objective is to minimize the weight, and we want to constrain the failure index of each ply shape, or ply, if you will. Now, the strategy I'm going to be covering in today's workshop, I'm not going to go into great detail regarding the strategy. Some of the values I pick, you might eventually ask yourself, how did I arrive at these values? How did I arrive at these different steps? This is all discussed in the appendix. It will take me maybe 1 or 2 hours to go over the strategy that we go over today. To keep this workshop as short as possible, I'm going to skip a lot of the discussion regarding the strategy. So here, I'm not going to discuss how I arrive at the filter values I go over in this workshop. I'm not going to discuss the strategy I use in this workshop. I refer you to the appendix so you can go at your own pace and in your own time go over the strategy I employ in this workshop. I will give you a quick summary though. The one thing I will cover or discuss right now is what briefly the strategy is to create the various ply shapes. Now, in the previous workshop, what we went ahead and did is we looked at all the failure index results for the plies and we stored them in the .ply files. So .ply 001 and then 2, then 3. That's where we stored the failure index constraints or the failure index values. You could do this for ply stress or ply strain value, but today we're working with failure index constraints or values. Here, what we're going to do is we are going to construct ply shapes that follow the contours of the failure indices. So here, if around the hole, maybe you want to create a ply shape that follows this contour. That's the strategy we're going to employ. So here is just one example of the ply shapes we're going to be building. And in the appendix, I go into more reasoning why this is an effective strategy for creating your ply shapes. Now, I think we are ready to start the tutorial. Let me just go ahead and say one quick thing before we go on. If there's ever a moment when you want to perform an optimization and you have a question, you're always more than welcome to contact me at this email address. Maybe you want to start learning how to use machine learning for FEA, finite element analysis, or CFD, computational fluid dynamics. You can come to me and ask me how to approach your optimization problem. Now, this tutorial is broken down into different parts. In the first part, we're going to go ahead and create the ply shapes. We're going to then ask the question, okay, for each ply shape, how many of each ply shape do I need? So this is where we perform the ply number optimization. And then at the very end, we are interested in actually looking at what the plies look like. So at the end of this whole workshop, we're actually going to look at 3D representations for the ply thickness and the coupon. So let's go ahead and get started. And just one other reminder, the Sol 200 web app, which we are going to be using today, is not only limited to composites optimization. You can perform machine learning in the web app. You can perform multimodal optimization. You can create XY plots. You can create beam cross sections with this tool. And over the coming years, you're going to see more and more capabilities added to this web app. So just know that this tool is not only for optimization. It's becoming a multi-purpose tool for MSc Nastran. Now let's go ahead and get started with creating the ply shapes. So you can either use your own composite model to follow along, or you can download the tutorial files that I'm going to download right now. As always, I always encourage you to start with a clean and empty downloads directory, and this is mainly to prevent confusion with other bulk data files. So here is the workshop for today's tutorial. I'll go ahead and click on starting PDF files link. And then if we go ahead and download this right now, this is my set of starting files. Now remember, in the previous tutorial, I've configured the bulk data file to perform a topometry optimization. So here you see a few tomvar entries, but we didn't really perform the topometry optimization. What we went ahead and did, we stored all the failure index values in these .ply files. So here are the .ply files, or the failure index values for the 90, the positive 45, the negative 45, and the 0 degree layers. Now, what I'm going to do is go back to the web app. I'm going to open the viewer web app, and this is where I'm going to upload all of this data right now. So think of it of us combining the data right now. So we're going to upload the bulk data files, and then we're going to upload the .ply files that I showed you a moment ago. So let's go ahead and navigate to that directory and upload these .ply files. Now, these .ply files were manually created. Alternatively, if you want to perform the topometry optimization, you can go ahead and do that also. But when it comes to ply stress, ply strain, or failure index values, I find that it's better to skip the topometry optimization, and it's better to manually create. It's better to store the ply stress, the ply strain, or the failure index values in these individual files. So that's what we did here. Let's go ahead and jump over to the ply shape section. Here, let's quickly configure the ply number optimization. If you look here in this box, all the bulk data entries that this web app is going to generate, they're going to be stored in this box. So as an example, suppose I specify a ply thickness for the 0 degree layer. As soon as I start typing in information, I get the equivalent bulk data entries in this box. You'll see that I get the thickness variables here, dvpro1, desvar, and then I get the ply number variable y1 created for me here. And all of this is done automatically. Let me go ahead and now specify a failure index for this layer. So if I click on failure index, and then I click on the failure index for just the plies, if I scroll down to that layer, and if I type in 0.95, you'll see that, well, not right now, but later on, you'll see that I get constraints for DREST1, and the D constraint entry will be created here. Now, here is a table, the ply number table. This corresponds to the pcomp entry. If I scroll back to the presentation, if I show you this, this table represents layer 1, 2, 3, 4, all the way to 9. So this is the top layers, and then here in the middle, or at the end of the table, is the core. Leave the core untouched. Do not modify any of these values. Do not specify a failure index. The failure index is only for the plies. So if you recall, the first 4 layers are going to remain fixed. You should not specify a ply thickness for the optimization. But the next 4 layers, these 4 layers will vary during the optimization. So I will specify a ply thickness for the ply number optimization. I will specify a max failure index of 0.95. So some of you might be thinking, usually we want to limit the failure index to be no greater than 1.0. You can do this, but there's a small challenge to this. Sometimes the optimizer will give you 1.01 and will say this is okay. But for us, we don't want that. We want to say that maybe the upper bound is no greater than 0.95. So the optimizer might come at a value at a 0.951 or 0.952 or 0.96. So this is what we want. We don't want to go greater than 1.0, but the optimizer might sometimes go greater than 1.0. So in order to avoid that, we just reduce the upper bound to 0.95. So that's why you see me here using 0.95 instead of 1.0. Now, I think we're ready to go ahead and create our first ply shape. So let me go ahead and minimize this. And let me go ahead and change the view to be the front view. Let me use the mouse to move this left and right. And here we're ready to create our first ply shape. So here, if you want to create a ply shape, just click on this plus icon and then move this slider. This slider is going to be filtering the values that you've uploaded in the .ply files. So right now the filter is filtering out all of these different values. This is an automated approach to creating your ply shapes. Alternatively, if you want to custom tailor your ply shapes, you can also click on this icon called pick mode, and you can go ahead and go to the screen, click and hold down the left mouse button, and you can spread the ply shape as you see here on the screen. Remember, blue is the ply and gray is no ply. If you want to remove the ply, click on this erase or remove icon. The pick sphere becomes red. Left click and hold the mouse button, and now you can scroll the sphere and you can remove the ply shape as you see here on the screen. Now, let me go ahead and create 2 ply shape candidates for the 90-degree layer. Let me go ahead and create 2 ply shape candidates for the 45 and negative 45 degree layers. You'll see here that since we created 3 45 degree ply shape candidates, we also get 3 negative 45 degree ply shape candidates. Remember, we want to create a balanced laminate, so we'll have an equal number of positive and negative 45 degree plies. And here for the 0 degree layers, we'll go ahead and create 4 additional ply shape candidates. Now, in the workshop, in the appendix, I give you more information about how we select the filter values. Now, I encourage you to take time after this workshop or before this workshop, refer to the appendix so you can get an understanding of why we are picking these specific values. So here, let me just navigate. Right. So if you look at the appendix, refer to this question: what filter values to use? This is where I give you more information regarding what values to use for these filter values. But here, my current strategy is to select the halfway point for the filters. If you wanted to, you could create additional ply shapes for additional filter values. Here, I'm just giving you a few examples of additional filter values to use. So here, for these 2 rows, if you will, I'm using 25% of the filter value. For these 2 rows here, I'm using 50%, and for these other 2 rows, I'm using 75% filtering. So again, refer to the appendix. You can really pick what you think is best for your scenario, but here I'm just using 50%. Let me repeat the process for the 45-degree layers, and let me do this for the 0-degree layers. So here we're picking 50%, and then for these other 2, maybe I'll pick just maybe 25%. And then here, I think I'll use that. Okay. So now that we did this, there's one big problem with these ply shapes. For some of these ply shapes, we cannot manufacture them. If we look at the hole, you see that for the hole, trying to produce this ply, if you will, is very difficult. So in a moment, what we're going to do, we're going to clean this up a little. One additional thing about these ply shapes, here let me zoom out. So fit model here on the right and move the model with the right mouse button. Here, let's suppose we create a ply shape like this. Let me take an image of this. And let's go ahead and copy this into the PowerPoint I have open here. And let's have a quick discussion on this ply shape. Let's suppose that we separated both of these ply shapes and we find out that we need 5 plies for this ply shape and we needed 10 plies for this ply shape. But since right now the ply shape includes both of these pieces, both of these ply shapes are going to be optimized together with a variable, we'll say y1. At the end, we'll get a variable number of 10. And this is not good. That means that during the optimization, it saw that we needed 10 plies for this piece, but since this ply shape is included together, we need 10 pieces for both ply shapes, if we will. Whereas if we did this, let me just go ahead and delete all this. If we were to separate these ply shapes, suppose we did this, and then we have a variable y1 for this ply shape, and then a variable y2 for this ply shape, then we'll arrive at different ply numbers for both of these pieces. And that's what we want. We want to break up this ply shape so they're 2 separate ply shapes, and we get 2 separate ply numbers for each of these ply shapes. So let's go back to the web app, and let me show you how to do that. Let's go ahead and click erase. And here we get this red sphere. Left click and hold the mouse button, and then just drag the sphere. And here you can see I'm finally removing the ply from around the hole. And that leaves me with this fully intact piece on the left. So I'm just going to repeat this for the 90, the 45, and the 0-degree layers. So let's go ahead and go here. This ply shape doesn't have anything here, so I'll skip that. And let me just inspect the other ply shapes. Right, okay. So now we'll repeat the process for the holes. We want to separate this ply shape. So for the third candidate for the 90-degree layer, I clicked on this erase or remove icon, and I just go ahead and move the sphere. If you want to move faster, here on the right, there's an input box called picking sphere radius. You can resize the size of the pick sphere. So you'll notice that the pick sphere is a lot larger. Let me go ahead and now use this larger pick sphere to remove this ply shape. And remember, the goal is to separate the ply shapes. My only ply shape for this candidate is here around the hole. And let me go ahead and repeat this here. And then for this exercise, I think I'll go ahead and delete this 5th ply shape. So I'm only left with this ply shape that you see here on the screen. And let me go ahead and now go over this. Now, if you look here, if we try and manufacture this ply shape, we have to create or cut the ply shape in this far top left corner. Maybe we don't want that. So here with the edit icon here, the yellow icon, I click on it, the pick sphere turns yellow. Now I can just drag the pick sphere and spread the material. Here, the goal for me is to create a ply shape that I can manufacture. And this was done for the 90-degree ply shape. Let's go ahead and repeat the process for 45 degrees. So we'll just go ahead and do the same thing. We'll go ahead and spread the ply. And this is something that we can better manufacture. So if we look at the P-Comp-G zones, here in the top left-hand corner, there's a button. Let's go ahead and click that button. You can see that as we manipulate these ply shapes, the P-Comp-G entries are being changed automatically. This is what the P-Comp-Gs currently look like. If I look at the bottom of this section, you can see that I now have all these different P-Comp-G entries, and all the 2D elements have been updated. So here you see that the IDs have been updated. All these P-Comp-G entries are necessary to define all these different ply shape candidates I'm working with so far. So let's go ahead and turn that off and continue. So this is what the 90-degree ply shape looks like. Maybe let's go ahead and work on the ply shape for the hole. Here is another example. Maybe we don't want a ply shape that looks like this. So we'll go ahead and go here, and we'll reduce the size of the pick sphere. Maybe it's a little too small. Let me go and maybe use 1. Okay, that's a little too big. Let me use 0.5. And then once I resize the pick sphere, I can just resize the ply. And you'll see that I'm spreading the ply around the hole. And the reason I'm doing this is because this ply shape is a lot easier to create than the previous ply shape. And let me go ahead and jump to the next 45-degree ply shape. And then here I'll click the edit icon, and I'll just do the same thing. I'll just go ahead and spread the ply around the hole. And then you'll see that this ply shape is a lot easier to manufacture. And then here, let me investigate the 0-degree layers. And I'm using these checkboxes here in the far left-hand column to display the different ply shapes. So here we're looking at the ply shape for 0 degrees. And here, I guess, instead of building or manufacturing this ply shape, I want to build something that's a little easier. So let's go ahead and move the pick sphere around the hole, and you can see all the elements are turning blue, indicating that that's where the ply shape is being applied. So let's go ahead and just go around the entire hole. And if you ever make a mistake, that's okay. What you can do is just click the remove icon. So here, let's suppose I make a mistake and I accidentally apply the ply here. That's okay. Just click on the remove icon. The pick sphere turns red. And then you can move that little sphere around that set of elements and the ply is removed. And then remember, whenever you make an adjustment to the ply shape, the P-Comp-G entries are being updated automatically. So here you see that lingering piece of the ply shape. It's been immediately updated to the P-Comp-G entries. And remember, if I want to undo that, that's okay. Let's just go ahead and remove the ply shape. And then if we look at the P-Comp-G entries, they will be updated automatically. Now, let me see here. Let me zoom out a little. And let me flip through the various ply shapes. For the 90-degree layers, this is what we have so far. We have a fully continuous ply shape that spans the entire coupon. We have this next ply shape candidate, and then we have a ply shape candidate for the hole. The same is true for the 45 and negative 45-degree plies. This is what those ply shapes look like. What about the 0-degree plies? This is the first candidate, the second candidate, and maybe we don't want this ply shape candidate. What can we do here? We can resize the pick sphere, maybe 4. We can spread the materials so we can create a ply shape that we can manufacture. Here, I'll leave it up to you to decide if this ply shape is okay for you. Alternatively, you can spread the ply to build something that is easier to manufacture. Now, Here we look at the hole and we have a thin shape, if you will, around the hole. And then for the next ply shape candidate, that's what that looks like. If you want to modify this ply shape, you can just, again, spread the ply. You will be limited depending on what your mesh looks like. If we go back to the workshop in a moment, and I'll do that right now, you'll see that when we're spreading this ply shape, we're actually applying the ply to these various elements we defined on the mesh. So even though you want to create a perfectly linear cut, this may not be possible with the mesh. So here, let me just scroll to the very top and show you what the mesh looks like. Right. So here, for this section, we can create these nice linear cuts, but for this region, it might be a little difficult just because it's a little jagged. So you do have some options you can play with. You can either accept this compromise and move forward, or you can spread the material even more. So here's another example. Here I'm spreading the material, and you'll notice that now I'm getting these nice linear cuts. You can do this, and it's totally up to you. Here for this exercise, maybe that's what I'll do. I'll just go ahead and move this ply shape here. And then I'll purposely leave it like this. I'm not going to update the other side. The reason I'm doing this is because I want to show you how flexible it is to create your ply shapes here. If this was if you were aiming for consistency, I would repeat the process for this bottom portion of the coupon. But since, again, I want to show you how flexible it is, I'm going to leave the ply shape here for now. Let me go ahead and zoom out. And let me go through the various ply shapes. So, okay, that's what that ply shape looks like for the 90-degree layers. This is what it looks like for the positive and negative 45-degree layers. And then for the 0-degree layers, this is what the ply shapes look like so far. Remember, we're using filtering values that are 50% of the slider. Here, for this really exotic looking ply shape, I'm using a filtering value that's about 25% of the width of the slider. And again, the appendix in the tutorial goes into more detail regarding what the strategy is here for these values in the filter. Now, if we look at the PCOM-G zones, if you will, this is what it currently looks like. I need to define PCOM-G 2, 3, 4, 5, 6, 7, 8, 9, and 10 in order to capture all of these different ply shapes I've created so far. And remember, anytime you make an edit, all the PCOM-G entries are automatically updated for you. And now let's go ahead and look at the ply number optimization, because I believe this is pretty much all done for us automatically. You see that all the ply shape candidates we've configured, we've specified what the ply thickness is for each of those candidates, so 0.125, 0.125, and so on and so on. Remember, for the core, there is no ply thickness, there is no optimization of the core, so that box is grayed out and left untouched. Now, what about the failure indices? Typically, the highest failure indices are located at the outer plies. So you can think here, the greatest failure indices are greatest in the outer plies. But in this workshop, I ended up just constraining the failure indices for all the ply shape candidates. So let's go ahead and go back to the web app rather. You can see that I specified 0.95 as the upper bound for all of these failure indices. Make sure that this row reads failure index FP for direct stresses and strains. You don't want to accidentally specify the failure index for the interlaminar shear stresses. So let's go ahead and look here and make sure I've filled out. And for the core, do not specify an upper bound for the failure index. This failure index only applies for the plies. Now, here are some additional optimization results that we did not use today, but I think it would be worth mentioning real quick. Now, sometimes the plane where you define your grids or your nodes, that node plane defines the mold line for your composite. And maybe you don't want your composite thickness to intersect the mold line. So what you could do is the following. Here, let's suppose that this surface represents the nodes, your 2D elements. That's what that's representing. Or I made a mistake here. The node plane, the mold line is this section, if you will. So this is the mold line. So this plane, if you will, this is where you have all your 2D elements. This is where you have all your 2D elements. You have some offset options. You can either offset the composite to be below the mold line, below the 2D elements, or you can offset the composite to be above the 2D elements. In this workshop, we're only dealing with the default option. So the default option looks like this. So basically, half the thickness is going to be on the top of the 2D elements, and then the other half of the thickness is on the bottom half of the 2D elements. So again, we're using the default option. Also, if you have some percentage requirements for your plies, maybe you wanted to use a minimum of 10% of 0-degree plies, you can specify that here. So you just type in the value 10%. And then your necessary, I believe it's derefs 2 entries are created. So let's go ahead and scroll down a little and see if we can find the derefs 2 entries. And let's go here. Right. So here are the derefs 2 entries to define that percentage requirement. But here, all we have to do is just modify this input box, and all the entries are managed for me automatically. If you had a limit on the total thickness of your composite, you can specify that information here in the lower and upper bounds. If you wanted to switch from asymmetric to maybe an asymmetric laminate, you would change to the laminate option. Here, I'm going to leave it as a symmetric laminate, and I'll go ahead and click on Save New Entries. And then here in the next box, New Entries, make sure that you have entries here. These are the newest bulk data entries that are going to be added to your bulk data files. Let's go ahead and click on Download. And here, let's go ahead and look at this new set of bulk data files. But before I do that, let me do something. This set of files or bulk data files, they've been partially configured for a ply number optimization. Right now, we just spend a good deal of time configuring the ply shape candidates and part of the ply number optimization. What I need to do now is finish configuring the ply number optimization. So that's why I opened the optimization web app. Now, in the downloads directory, let's rename this new zip file that was downloaded. Let's call it ply shape output. And this is why I'm calling it the ply shape output. If we look inside of this zip file and we open up the design pcomg files, all of the pcomg entries I need to define and express the ply shapes are created here. So you can see that the G plies are here. They've been created for me. Also, all the definitions for the ply number optimization, all the definitions for the failure index constraints, they've all been created for me and stored in this bulk data file. One additional thing, if we look at the original analysis model, before it'd be worth opening the original bulk data file, the 2D elements were all pointing to pcomp1. So you see they all are using ID PID1. But now if we look at the updated 2D elements, you can see that the PID is actually going to vary. This set of 2D elements are going to be using PID2, which is pcomg2. This set of elements are now using pcomg3, and you'll see that as we go through these various elements, they're all pointing to different pcomg IDs. So some of these are using pcomg6, and eventually you'll find that they're using pcomg7. So here we see pcomg7. These other elements are using pcomg8, 9, and 10. So you can look back at the viewer, click on ply shapes, and click on pcomg zones. And here, this is what's been done. Each element is now pointing to a different pcomg element. Again, this is done to capture all the different ply shapes that have been created. Now, let's go back to the optimization web app. Let's go ahead and upload the ply shape output bulk data files. Now, again, the ply number optimization has been partly configured for us. We have all the definitions for the ply thickness variables, for the ply number variables. The objective that we defined a few workshops ago, that's still here. All the constraints, the failure index constraints for all the ply shapes have been defined for me here. The only thing we have to do now, we have to assign these failure index constraints to these subcases. Now, here I've clicked on the subcases section, and I'm going to list at most 200 rows. And now, what I'm going to do is I'm just going to mark all of these checkboxes so I can assign all these constraints to the subcases. Now, you can go checkbox by checkbox, but this might be a little slow if you're dealing with thousands of subcases. So there's an alternative. Here in this box, only display the subcases you want to work with. Either uncheck or check all the visible checkboxes, and this will automatically assign all your different constraints to each subcase. So here we've assigned all the failure index constraints to subcases 1 and 2. And let's go ahead and scroll here and just make sure all the checkboxes have been marked. Great, perfect. Let's now go to the exporter and click download files. And we'll rename the zip file 3 ply number optimization. So let's go ahead and rename it ply number. And then here, let me just add ply number optimization just so it's clear to us what's going on here. And we'll go ahead and extract the contents. And once we open that directory, we'll go ahead and click start MSC Nastran to start the optimization. Now, there's one detail I want to mention. So in most of my recommendations for optimization, I always encourage everyone to start with a feasible design. And then this will oftentimes yield a solution that's also feasible. If you start with an infeasible design, the optimizer then has to navigate through the infeasible design space. And now this is a problem because sometimes you will get a feasible design or you will get an infeasible design. A feasible design is a design where all the constraints are satisfied. So this is a problem for us. If we start with an infeasible design, sometimes the optimizer cannot find a feasible design. So you're stuck with this infeasible design after the optimization. So I always encourage everyone to start with the feasible design. Now, from experience, this is what I've noticed. If you start with the feasible design for ply number optimization, and the way you do this is, say your Y1, which is your ply number variable, you start with 100 plies. You'll most likely end with the feasible design, but this is what I ended up finding out. This will yield a suboptimal solution, which is not good because we want to look for the best possible number of plies. So what's the alternative? This is what we end up doing today. For the infeasible design, or rather, we start off with an infeasible design. We start off with a ply number variable that I believe is 0.01 plies. So this is a very thin number of plies. So what we're doing here is saying, okay, start with a very thin ply, size up the plies, so we eventually get a feasible design. This surprisingly yields a optimal solution. So that's why you see in the optimization results where the optimization has finished, you'll see that the ply number variables, so let me go ahead and display the ply number variables. You'll see that the ply number variables start at a fraction of 0.01. If you go back to the viewer, if you go back to the ply shapes, if you go down to that ply number table, which is this table here, you'll see that the initial number of plies has been set to 0.01. This was done on purpose, so we start with an infeasible design. We then let the optimizer inflate or size up the number of plies. So here you see we started with the fractional number of plies of 0.01, and you see the optimizer start to inflate or increase the number of plies. And this is what we get at the end. We see a number of things. Number one, the objective. Since we started with an infeasible design where the constraints are violated, the optimizer has to add more and more plies. So this is why you see the objective or the mass increase, because the optimizer is having to add more and more plies. Since the plies were originally very, very thin, we're exceeding the failure index values. This is why your max normalized constraint is a very large number of 7.36. We're actually exceeding the upper bound by 700%. Here you see the optimizer work towards minimizing, or not minimizing, but reducing the violation of the constraints. We have 500% here, 400%, and eventually we get to a very small value. Here we're violating the constraints by about 40%, and then here eventually we get a negative normalized constraint value. So here we're now satisfying the constraints by 3.5%, 3.5%, and by the end we're satisfying the constraints by 10%. If you wanted to confirm that we're actually satisfying the constraints, there is a tool in the web app. If you go back to the optimization web app, you go to results, you go to responses, you can upload the F06 file. So let's go ahead and upload the F06 file for the ply number optimization. Click upload, and then click on maximum constraint for each design cycle. So here on the far right hand corner is a column, normalized constraint. Here the normalized constraint is 700%, 500%, 400%. You'll notice that these values are matching up with the values from the max normalized constraint plot. So now that we know where we can look at the max normalized constraint values, we can then refer to the column value. In the value column, we get the actual failure index value. So you see for the very initial infeasible design, the max failure index is about 8, which exceeds the upper bound of 0.95. And you look that the failure index is reduced from about 8 to 6 to 5, 4, 3, 2, 2, 1, and eventually we get to a value that's less than 0.95. So again, you can use this responses web app to debug or look at what your responses are doing during the optimization. You see the optimizer started with an infeasible design and then continuously added plies to make this composite a feasible design. And like I said before, if you start with an infeasible design for ply number optimization, you'll actually reach a better solution than if you were to start with a very thick number of plies, which often yields a suboptimal solution. Now, here, let's look at a few things that's happening. For ply shape Y10, if you look here on the table, this is what this ply shape is. It's G ply ID 184000. I'm going to copy that, and I'm going to go back to the viewer. I'm going to search the web app for that ID. And what I want to do is I want to look at that ply shape. So the optimizer is telling me that I need 2 plies for this ply shape. And if we hover over that, you see the value of 2. Again, we get a value of 2. the optimizer is telling me that I need two ply shapes, or two plies for that ply shape. Now, let's see. Let's look at this a little bit more. You can repeat the process for Y9, Y7, Y6, Y4, and so on and so on. Let me make a comment about Y8. So Y8 is going to be this ply shape. So let me go ahead and copy that G ply ID. Let me go back to the viewer and let me search for that G ply. Once I find it, I'll go ahead and display that ply shape. So here, for this ply shape, I'm being told that I need 0.4 plies. And you might be thinking, okay, so we need less than one ply. This is where we can say, okay, this ply shape is possibly negligible. What the web app will do, it will actually remove that ply shape automatically because it's been deemed negligible. So if we zoom out of here, let me go ahead and show you what's happened in the updated bulk data files. So if you upload that directory where the ply number optimization was performed, if you open up workspace C, you'll see that the pcomg entry looks bigger than it did before. And let me actually show you what it looked like before the optimization. So here on the left is going to be the original pcomg entry. And then here on the right, it's going to be the new pcomg entry. So let me just try to resize these. Right. So some of these entries have been repeated multiple times. And here, let's go ahead and look for gply ID 1840. So I'll search 1840. And that's going to be pcomg3. And then here, let me do that and scroll here. Right. So for that ply shape, we get told that we need 2 plies of that ply shape. If we look here on the left before, that ply shape was only listed one time. So 184000. But after the ply number optimization, we find that we need that ply shape to repeat 2 times. So you see that ply shape 184000 has been duplicated 2 times. And that's what's been done for all these other pcomg entries. The pcomg entries have been updated to reflect the number of plies that have been determined during the ply number optimization. I think it might actually help if I show you what the plies look like right now after the ply number optimization. So if I go ahead and open up a new viewer, I'm going to go ahead and upload the newest set of bulk data files. So go to the ply number directory, go to workspace C, go ahead and open those files and upload them to the viewer. Click on the model display panel here on the right hand side. And in a moment, you're going to see that the web app is going to be computing all the different thicknesses for the plies. So depending on the size and the number of plies that you have in your model, this could either take a few seconds or it could take 1 or 2 minutes. So you see all these different checkboxes. This is all the plies that are being computed for this composite coupon. Let me go ahead and reorient this model. And let me go ahead and search for that gply ID, which I believe was 18400. So here in the property ID, or actually the gply ID column, I'll search for that ply shape, 18400. And let's go ahead and take a look at what that ply shape looks like. So that's going to be this ply shape. And let me turn off all of these different pcomgs. You can either go checkbox by checkbox, or you can just click this icon here to hide all these different pcomgs. And then I think, let me reset the table and do that again. Let me hide all the different pcomgs and let me search for that gply 184. And this is what that gply looks like. And then if I display the second ply shape, that's what that ply shape. So if we zoom in, actually, you can see that here we have 2 of the same ply shape. If it's a little difficult to differentiate the ply angles, you can go ahead and click on this icon. This will assign a unique color to each different angle. So here, since both of these plies are 0 degree plies, they're both colored 0. Now, let's see what else. Since this composite is symmetric, whatever happens on one side is going to happen on the other side of the composite. So if I turn on the mirror plies, and if I zoom out a little, you'll see that here we have the 0 plies here on the top and the bottom, and in the middle is the core. If you want to look for the core, let's go ahead and reset the table. And then the color, I'll recolor this. And the core layers are colored this beige color. So here, this is the beige layer. So let's go ahead and turn on the core. And this is what our composite looks like so far with these different ply shapes. So remember, when you're displaying different ply thicknesses, there will be some time to regenerate the ply thicknesses. So that's why you find these weird gaps, and then eventually they get filled in. So now let's go ahead and display all the different G plies. And let me turn off these plies for now. Let me list only the PCompG entries. Let me fit the model, and let me zoom in a little. Right, let me zoom in. And now let me display all the ply thicknesses. What I want to show you is a literal view of the PCompG entries. So then this might be this region, or maybe not. Let me zoom out. Right, okay, maybe all the action is going to happen here towards the hole. Now let me zoom in. You see that we have different steps. This is what the PCompG entries look like. But maybe you might be more interested in looking at the plies as if maybe they were tapered. There is an option to look at the plies in a tapered way. So here, let's go ahead and open the model display panel. Let's go ahead and hide all the different thicknesses so far, and let's search for the G plies. And now let's go ahead and display all the different plies, and let's go ahead and hide it. So now, if you look at the G ply instead of PCompG, when you look at the G plies, you see that the plies are actually tapered. And this is a great way to confirm what the results of your ply number optimization look like. Now, let's see, what else is there to do? Let me go ahead and go to the table. So when you perform this optimization, you might get a different solution. And that's okay, as long as your composite has less mass than before. So the question for us right now, if the initial composite had this mass, what's our composite when we perform the exercise? So let's go ahead and open up the F06 file. And remember, our objective was to minimize the mass. So here we'll go ahead and look at what the mass was at the very end. The mass was, actually this mass might not be accurate. This mass assumes that all the ply shape candidates were included in the final composite. But if you recall, we actually performed an elimination. So what I'm going to do is I'm going to run Nastran on the updated bulk data files, and I'm going to inspect what the objective was in that model. So let's go ahead and scroll here. And if we look here, we'll see that the mass either dropped or increased depending on what the elimination procedure was. And here you see that the mass was actually increased very slightly, which is okay. Let's just go ahead and copy this mass. Let's go ahead and paste it here. This is the total mass. The mass of the core is going to remain the same. And then let me open up Excel so we could do a quick calculation to determine the mass of the plies. So maybe let's go back here. And while Excel was loading, let me mention that sometimes when you eliminate some of the plies, you actually increase your highest failure index. So here, the current normalized constraint is negative 1.38. This could actually increase to a positive value. So let's go ahead and look at what the new value is. So now we're exceeding the failure index by a little bit, but this is okay because once we do the stacking sequence optimization, we'll actually see that we're still within the bound of 0.95. So here, let me go ahead and copy these values. And then let's go ahead and do a subtraction equals that minus this. And let's go ahead and copy this value. And you'll see that the mass is actually better than the original mass. So as long as you get a better mass than before that's feasible, you are properly following the strategy that was shown in this presentation. If you get a higher mass, I would double check. I would actually go through the tutorial again just to see where the procedure may have been done a little differently. But as I say, as long as you get a better weight, you're following the strategy properly. I remember in my early days of optimizing, I was always focused on finding the converged solution. I was always focused on finding the global solution. Sometimes you do not have time to do that. Alternatively, if at the minimum you were able to minimize the weight, that is still a victory in my opinion. Now, one last thing. Let's look at what the failure indices look like. And here, I think, let's open Patran. And let's go ahead and investigate what the failure indices look like. Remember, we performed this ply elimination. Now, this ply elimination will sometimes increase the failure index. So you might accidentally go beyond the upper bound of 0.95 when you eliminate some of these ply shapes. This is okay because in the stacking sequence optimization, which is the next tutorial, that's going to bring back down or reduce the max failure index. So let's go ahead and open Patran. We'll go ahead and import that coupon. So we'll go ahead and go to Workspace C and open that set of bulk data files. And we'll go ahead and go to Analysis. We'll click on HDF5, select Result File, navigate to the same Workspace C directory, select the H5 file, and click Apply. And then when you go to Results and Fringe, you should see two subcases. Let's look at the max failure index for subcase 1. So we'll go ahead and select that subcase. We'll look at the ply indices, and now which plies? You want to look at the max failure index for all the plies except the core layers. So here, this is gply 111000. If you look at the viewer, basically each of these different plies has a different gply ID. And that's what we're selecting here. We're selecting different plies in order to look at the results. So select all the plies except the core layers, which are ID 191000 and 2191000. Let's go ahead and look at what the max failure index looks like. Now, typically and personally, I do not like looking at the averaged results. So what I'm doing here is I'm going to the first, second, third, and fourth icon. Here in the averaging definition for domain, click none. This will disable the averaging. And this is what we have. The max failure index for subcase 1 is now 0.75. Let's go ahead and document that. 0.75. So this is okay. We're less than the upper bound of 0.95. Let's look at the second subcase. Let's go ahead and click apply. And let me move this a little. And you see here that we've actually gone above the upper bound of about 0.95. We're actually getting a bound or a new max failure index of 0.975. So let's go ahead and document that here. 0.975, and we'll say this is okay. And remember, typically, to be exact, maybe we want to specify the upper bound is 1.0. But sometimes what you'll see the optimizer do is it'll actually go a little bit beyond the upper bound. Maybe you'll get 1.01. Maybe we don't want that. So one strategy is to use a new bound that's far away from the actual bound we want. So during this exercise, that's what we did. We used a reduced bound of 0.95, and here it paid off because even though we eliminated some of the plies, we're still less than 1.0 as you see here on the screen. Now, one last comment. Remember, you might be focused on getting the same solution as was demonstrated in this tutorial. So that would be this mass. You might want to get the same solution as shown in the instructions in this tutorial document. I will say that you will most likely not get the same solution, but as long as you get a mass that is lower than before, you have successfully used the strategy that's shown in this tutorial. In the end, I believe that if you get a mass for the plies that's around this value of 1.7, I think you've gotten pretty close to the solution in this workshop. So again, do not try to get the same solution. Just try to get close. Now, I think that's the end of this tutorial. Just a few last comments. In the next tutorial, I'm going to show you how to perform a stacking sequence optimization. So if your plies are together, we're going to separate them out a little bit more just so we get a more homogeneous cross-section for the composite thickness. So again, that's coming up in the next tutorial. And I think it'd be good for me to end it off here with my contact information. As always, if you had any questions regarding what you saw here today, you're more than welcome to contact me here at this email address. And thank you so much for watching.